In this video, we're diving into the world of waves, what they are, how they work, and why they matter. Whether you're interested in light, sound, strings, or springs, waves are everywhere, and your understanding of them starts here. A wave is a disturbance in a medium that propagates outward from a source point. And when I say a disturbance, I mean that the particles within the medium are temporarily displaced from their equilibrium resting position. We would measure these disturbances by measuring the displacement in the medium. So, if we were to have a water wave here, without a disturbance, it would have a flat, calm level that we would call its equilibrium point. But this disturbance propagates through the medium and displaces the water particles from that equilibrium position. They'll either be displaced upward or downward, so we would measure the displacement of this water wave as a delta Y. There are two major classifications of waves: mechanical waves and electromagnetic waves. Mechanical waves require a medium to propagate in, like air, water, or a solid. These types of waves would include water waves, sound waves, or earthquake waves, seismic waves. On the other hand, we could have electromagnetic waves, which do not require a medium to operate in. Things like X-rays, microwaves, radio waves. These are electromagnetic waves that can propagate through a vacuum. It's important to note that waves do not actually transmit matter. They don't move the particles in the medium in an ultimate grand scheme of things. They only transmit energy, and this energy can be used to decode information by sending wave signals. For example, if we send wave signals at different timing, we could encode some type of signal that could be received, and this is called frequency modulation, or FM radio. On the other hand, we could modulate how strong a wave signal is. This is called amplitude modulation, and this is one way that waves can be used to transmit information. But notice something about the cube here in this diagram. You'll see that as the wave travels, as it propagates to the right, the cube doesn't actually move to the right like a surfer would on a wave or something like that. The particles in the medium are only temporarily displaced from their equilibrium position, but ultimately will just displace all around that equilibrium position. This is why when you're hanging out on a tube on the lake and waves continuously keep propagating through the water, you do not get pushed to shore. Notice that if we just track one point on a medium, that point does not actually travel with the wave. It's just temporarily displaced, as you can see here for this wave on a string. If a wave exists as just a single disturbance in a medium, we call that a wave pulse. This is like the example of cracking a whip or a large tsunami wave that builds up over time. On the other hand, if a wave is continuously generated throughout a medium, we call it a periodic wave. And this would be like an example of a sound wave or a light wave, or many ocean waves exist as periodic waves. In this diagram, you can see a pulse wave exists as a single disturbance, and a continuous wave exists as many multiple disturbances, one after the other. In this example, you'll see a wave pulse down at the bottom that travels through the medium. On the other hand, our continuous or harmonic wave features consistent multiple pulses being sent through a medium. Within the different classifications of waves, it's possible for the displacement of the wave to either be perpendicular or parallel to the direction of propagation, the direction that the wave is traveling in. If the displacement is perpendicular to the direction of propagation, we call that a transverse wave, as you can see shown in the top diagram right here. The displacement is vertical from the equilibrium position, but the wave is traveling to the right. On the other hand, we could have a wave where the displacement of the medium is in the same direction as the propagation of the wave. These we call longitudinal waves, and you can think of these as compression waves. Here in the diagram in the middle, you can see for this longitudinal wave that the medium is displaced left and rightward as the wave propagates to the right. Here you can see another example of longitudinal versus transverse waves. There are several wave parameters that characterize a wave. The amplitude describes the maximum displacement of a point in a wave from its equilibrium position. This is usually measured in meters, especially for like a water wave, but other types of waves can have different types of units depending on what displacement we're measuring. It's important to note that the amplitude is measured from the equilibrium position to the peak or trough. It is not the distance from peak to trough directly. That would be twice the amplitude, as you can see in this diagram. The amplitude of a wave is directly related to the energy transmitted by that wave. So if we have a wave that's spreading out, we expect for the energy conservation laws to hold, and as that wave spreads out, we would expect for its amplitude to decrease. The wavelength measures the distance between two identical points on a wave. This is measured in meters because it's a length, and it's important to note that the wavelength has to measure the distance between two identical points. So if we take a look at this diagram down here, you would see that there's a point here at the equilibrium position on the left and a point here at the equilibrium position on the right. But that is not actually measuring the wavelength. That is measuring half of the wavelength. These 2 points are not identical. As this wave travels to the right, we see that it is downward sloped for the point on the left and upward sloped on the point on the right. These are not identical points right here, so this red quantity is not the wavelength. The wavelength has to be measured either from peak to peak, or trough to trough, or from equilibrium position to equilibrium position, making sure that both points are identical. Here we see the wavelength of a wave that is traveling through a string under tension. The period is the amount of time that it takes to complete one full wave cycle, and this will be measured in seconds for the standard units. Every time that the wave undergoes one period, it travels one wavelength. If the period describes how much time it takes to complete one oscillation, we can also define the frequency, which describes how many oscillations occur every second. This would be measured with a standard unit of inverse seconds, which we call hertz. You can use Hz to abbreviate hertz. And the formula that relates the frequency and the period is that the frequency is the inverse of the period. We can now define the wave velocity, which describes the speed at which a wave propagates through a medium. The standard unit for wave velocity is meters per second, and sometimes this will be called the wave speed or the propagation speed. The wave speed can be calculated by taking the product between the wavelength and the frequency. Here you can see the wave speed shown as a vector pointing to the right, indicating that this wave in the diagram is moving to the right. Notice that the wave speed is not related to the amplitude at all. The wave speed is only dependent on the medium through which the wave travels. Notice that the wave speed is not dependent on the amplitude of the wave at all. A bigger wave does not mean that it's moving faster. Instead, the wave speed strictly depends on the medium through which the wave is traveling. In general, the wave speed can be solved for by taking the square root of some stiffness term divided by an inertial term. You'll notice that the wave speed is dependent on some wave properties, the wavelength and the frequency. But for a given wave speed, the wavelength and the frequency are inversely proportional to each other. So really the only thing that determines how fast a wave will move through a medium is the medium itself. For example, in a string under tension, the only thing that determines how fast the wave travels through that string is the tension force that it's under and how dense the string is. We can use this equation on the right to solve for the wave speed in a string under tension. Here, since the string is a one-dimensional object, essentially only having its mass distributed along a line, we use the linear mass density to calculate this wave speed. This linear mass density is measured in kilograms per meter, and of course, the force of tension is measured in newtons. Now that we know about the parameters that characterize different waves, we can represent waves on graphs in two ways. We could use a snapshot graph, which shows the displacement of the medium versus its horizontal position. These snapshot graphs must specify a time that we're looking at. So this is like what you would see if you were to take a picture with a camera. This is what you would see with your eyes. It's got a vertical displacement measured in meters on the vertical axis and a horizontal position measured in meters on the horizontal axis. And we have our time label here saying that at t equals 0 seconds, when I start my stopwatch, this is what the wave looks like. On the other hand, we could instead use a history graph to show what one position of a wave does over time. We can specify a position, like saying at a position of x equals 0, what does that wave do over time? Well, we would display our vertical displacement versus time in this case with a history graph. And we would see that one particular position goes up and down in this medium over time. If you have the time and you want to play with it, I strongly recommend these physics educational technology simulations. This one for a string under tension can really help you understand how the amplitude, frequency, and tension will affect the wave speed. A wave function is a mathematical representation of a wave that contains all of the information and all of the parameters to define any wave. Specifically, it describes the displacement of the medium with respect to position and time. This is a big equation, y'all, so we're going to go ahead and try to go through it one step at a time, but I really do encourage you to write it out yourself and label what each of these variables means. So first, we have the displacement here. For a water wave, this will usually be y, and that displacement would be measured in meters, but other types of waves can have different types of displacements that we measure. The next term is the position variable and time variable that we're going to use to keep track of this displacement. Displacement is a function of position and time. I have to pick a position on the wave to look at, and I have to pick a time that I'm going to examine this wave. That displacement depends on the amplitude of the wave. So the larger the amplitude, the larger we could get for a displacement. And this amplitude must match the units of the displacement. So if we're measuring y, this amplitude would be in meters. Then that will be followed by a trigonometric function that repeats itself, a sinusoidal trig function. And so we could either have a sine or a cosine here, but for now, let's just think about it as a sine, because that's a simple type of wave. And if we have a sine, that basically means that the wave cycle starts at an equilibrium point. That's how a sine wave looks. When I look at time equals 0 and position equals 0, the displacement of a sine wave is 0. On the other hand, if the wave happens to start at a maximum or a minimum, you could put a cosine here, and that would still mathematically describe the wave. Then in the argument of the trig function, we have a lot of variables here, but this argument will usually be presented in radians. So make sure you're used to using your calculator in radian mode. Here we have a 2 pi multiplied by x over lambda. This is called the spatial component of the wave. It's the part of the wave that depends on position. And this numerator variable will always match the variable in the function definition, and this denominator variable in the fraction will always be the wavelength of the wave measured in meters. Then that is followed by a minus plus sign. And so whatever this sign is here in the trig argument will define the direction that the wave travels. Now notice the convention here. If you have a minus sign in the trig argument, that means that the wave is traveling to the right. And if you have a positive sign in this trig argument, that means that the wave is traveling to the left. Then we have a 2 pi times f times t. F is the frequency and t is the time. This time variable right here matches the time variable in the function definition, and the frequency must be presented in hertz. This whole blue package we would call the temporal component of the sine argument. This is based on time. Lastly, we have a variable called the phase angle. We'll talk a little bit more about this in the upcoming slides, but for now you can just assume that it equals 0 radians. And in fact, notice that all of these terms in the sine argument have a 2 pi in front of them, a 2 pi, and that this phi is measured in radians. So you're going to always want to make sure that you enter radians into this trig function. Phi is known as the phase angle. And this basically defines how much the wave is shifted from its starting position. If you had a standard cosine wave like you see up here in the top, we would say that it starts at a maximum. But if we were to let that wave travel for a little bit or oscillate through its cycle a little bit, we would see that it could look like a sine wave a little bit later if we waited for it to oscillate pi/2 radians through its cycle. If we let it oscillate a little bit farther, this would cause for the whole wave to shift its horizontal position. And this is what the phase angle describes, the shift of the wave from its initial starting point. So if we have a cosine function and phi is equal to 0, that means the wave starts at a maximum. But if we have a phi equal to pi/2, like you see in this trig argument right here, we would see that the wave doesn't appear to be a cosine. It sort of looks like a sine function with a downward slope, but that is just indicative of how sinusoidal trig functions repeat themselves. If you shift by some phase angle, you will be able to describe the displacement of that wave given that shift at a particular position in time. Now that we've spoken about how to describe waves and how to show them on graphs, let's talk about what makes them special. Waves are distinctly different from particle-like objects because when waves collide, they pass through each other. If we take a look at the diagram at the bottom, we'll see that we have one wave traveling toward the other one, and as they overlap with each other, they don't bounce off of each other like billiard balls would. Instead, they pass through each other, and something special happens as they interact with each other. They combine to form a resultant wave. The superposition principle describes how two waves interact as they overlap with each other. Essentially, their displacements will add together, considering the sign of the displacement. We would call the two waves that are adding together the individual waves, and the total wave that we get when we add them together is called the resultant wave. We could describe the resultant wave with its own wave function that is the addition of the two individual wave functions. So if you take a look at the diagram at the bottom, here we have a stationary wave up at the top with displacement at varying positions. And then we have a traveling wave in the middle that's traveling to the right. Its displacement is also varying with position. So if we track this horizontal position, if we look at this point and try to add the two waves together, we will see that when the two crests are aligned, they create a resultant wave with an even larger amplitude. And when the crest is aligned with a trough, they create a wave with a resultant amplitude that is smaller than the individual waves themselves. When two waves combine to form a resultant wave with an amplitude that is larger than the individual waves, we call that constructive interference because the two waves are adding together. They're constructing a larger resultant wave. This results when the waves are aligned with each other, giving a larger overall amplitude for the resultant wave. If we have two waves that are aligned, we would say that they are in phase with each other. For two waves that are perfectly aligned, where their crests match up exactly and their troughs match up exactly, we would experience pure or perfect constructive interference, like what you see here shown in the diagram. Here's a representation of constructive interference for two wave pulses traveling in a string toward each other. We see that as the wave pulses come together, their displacements add together, giving a resultant amplitude that is larger than either of the two individual waves. But then the waves pass through each other. On the other hand, destructive interference occurs when two waves add together such that they give a resultant wave with an amplitude that is less than the individual waves. This would occur when waves are anti-aligned, giving a smaller resultant amplitude. We would say that the waves are out of phase with each other, and if they are perfectly anti-aligned such that the crests match up exactly with a trough, we would say that they would be experiencing pure or perfect destructive interference, like you see in the diagram shown here. For two waves that experience perfect destructive interference, if they're perfectly identical, the amplitude of the resultant wave will be 0. In this example, you'll see two waves traveling toward each other in a string under tension, and these two wave pulses, as they travel toward each other, they eventually interact, adding together their displacements. You'll see the one on the right was positive, the one on the left was negative, And as they overlap, they cancel each other out, but then they continue traveling in their respective directions afterward. Superposition can produce a mixture of constructive and destructive interference. While it's possible for waves to experience pure destructive or pure constructive interference, in reality, usually you'll get a mixture of these. The phase difference, or phase shift, measures the difference in phase angle between 2 points on a wave or the difference in phase angle between 2 waves. This will usually be measured in radians. 2 waves would have a phase shift if they were offset by some distance. And so one way to calculate the phase shift is through the spatial phase shift equation, which talks about 2 waves that are separated by a distance delta x. In that case, you could solve for the phase shift by using this formula, which relates the offset distance and the wavelength of the waves. On the other hand, if we have 2 waves that are being sent out from the same point, but with a time delay between them, we could calculate the temporal phase shift, which calculates a difference in phase angle based on a time difference. Here, delta t would be like the time delay between 2 identical points on a wave or 2 identical waves, and capital T is the period. Collinear waves are 2 waves that travel along the same line or direction in the same medium, but they do travel along the same line. They're collinear. The phase shift relates the wave functions of 2 collinear waves. If we imagine 2 waves like those shown here in the diagram, which are being sent into a medium with an offset distance of delta x, we could describe them both with their own respective wave functions. The first wave might have a y1 that's described with a simple wave function, and y2 would look very similar. It might have a different amplitude or wavelength, but we would say that its positional piece was shifted by some offset distance. If these are both dependent on the same positional variable, then we can change that position-dependent numerator to just be offset by some distance delta x, and now these 2 wave functions look very similar. That delta x will end up showing up as a phase shift when we compare the second wave to the first wave. The wave function for y2 could be rewritten to be very close in format to the wave function of y1, but including this phase shift. So here we took the delta x out of our numerator in the spatial piece and moved it over to the phase shift. We can see for 2 identical waves that are phase shifted, the resultant amplitude will always be between values of 0 at minimum and twice the amplitude of the individual waves at maximum. A 0 amplitude would be obtained for the case of pure destructive interference, and we would get pure destructive interference when our phase shift was an odd integer of pi. If we plug in an odd integer of pi into the superposition equation, it will return a resultant amplitude of 0. On the other hand, if we wanted pure constructive interference, we would have a resultant amplitude that was twice the amplitude of the individual waves, and this would be obtained for even multiples of pi in our phase shift. If we plug in 2 pi into this resultant amplitude equation, we would get a maximum amplitude. Waves reflect when they encounter a boundary and bounce back the way they came. We would call the incoming wave the incident wave, and the wave that is reflected back from the boundary we call the reflected wave. When experiencing a reflection event, the reflected wave will have the same wavelength and frequency as the incident wave. For a wave on a string under tension, the reflected wave will be upright if it reflects off of a free point in the medium. On the other hand, the reflected wave will be inverted if it reflects off of a fixed point like you see here. So if the medium is free to displace over here on the right side of this, then the wave will be reflected backward with a displacement that is the same sign as which the incident wave had. On the other hand, if the wave is reflected off of a fixed point like you see here, its displacement gets inverted upon reflection and sent back the other way. For example, here you'll see the wave reflection with inversion when the person is holding on to that end, keeping it fixed in place. The reflected wave experiences an inversion. On the other hand, without inversion, that would happen if the wave just reflected off of a free point, and we'll notice that the reflected wave travels backward with the same sign of its displacement that it had coming in. One example of a wave reflection is in an echo, where a sound wave encounters a boundary and is reflected back toward its source point. These reflections are useful for making measurements. If we know the speed of the wave, like the speed of sound in some medium, then we can calculate distances or make measurements of lengths by using that speed of the wave in combination with how long it takes for us to receive the signal. We would know that when we send out a signal, it has to travel one full distance downward and one full distance back upward before it is actually reached. So using that idea with the velocity as the distance over the time, we can use this to calculate the distance between a source and some boundary by measuring the time delay between the echo and when the signal was sent out. If we have a wave that is reflected back the way it came, and it interacts with an oncoming wave, we would say that those two waves are counter-propagating. They're traveling in opposite directions. And these two waves would be identical for an ideal case. And we could describe each of those waves, the incident and the reflected wave, with their own wave functions. Here, you'll see the wave traveling to the right is the blue wave. That's the incident wave. And we can use a minus sign to indicate that it's traveling to the right. And the red wave is traveling to the left. That's the reflected wave. It travels to the left. That's why it's got a plus sign there. And these two waves will interact. The reflected wave interacts with the incident wave to give the overall black resultant wave that you see here. Through some fancy math tricks, we can write out an equation for the resultant wave in this case for counterpropagating waves. And we see that the formula turns into one trig function that strictly depends on position and spatial components, and one trig function that strictly depends on time components. Such a math function gives rise to this black type of wave that you see here that doesn't appear to be traveling to the left or the right, but is still oscillating in place. We would call this a standing wave. A standing wave is a wave pattern formed by two identical counterpropagating waves. So again, the blue wave is our incident wave and the red wave is the reflected wave. And when those two waves interact, they give the resultant black wave, which is a standing wave. If we take away the incident and the reflected waves, the resultant wave appears like this, just a wave that's dancing in place, not actually traveling, it's standing there. These standing waves oscillate in time, but their amplitude profile doesn't move at all in space. These standing waves form distinct patterns of nodes and antinodes. A node is a point of no motion. That's these spots right here marked in green. You'll notice that when I just look at the displacement of that position on the medium, it doesn't displace at all. Its displacement stays zero the whole time. On the other hand, we have antinodes, which are marked in pink here, and these are points in the medium that experience a maximum displacement. They're constantly oscillating back and forth between a positive maximum displacement and a negative maximum displacement. We can generate a standing wave in a string under tension by using an oscillator setup like that one shown here in the top right. We can use an oscillator on one end to send incident waves into the medium that travel to the right, are reflected off of a fixed boundary, and the reflected waves interact with the oncoming incident waves to create a standing wave pattern. The simplest possible standing wave pattern that we could get would be one that would have one node on each end with an antinode in the middle. This is the lowest frequency standing wave mode that we could possibly get. It's the only pattern that we could get with one antinode and two nodes at the ends. This is required for a string that is fixed at both ends. And this lowest frequency mode we would call the fundamental frequency. Harmonics are multiples of the fundamental frequency that create a higher level standing wave pattern. N is the harmonic number which tracks which standing wave pattern we're looking at. The fundamental frequency has n equals 1, and it looks like that you saw on the previous slide. But we could still get standing wave patterns that have a node at each end at a higher frequency. For example, the second harmonic would have an n equals 2 number, and it would have one more node in the middle with 2 antinodes now. Going to higher harmonics from there, like the third harmonic where n equals 3, we would have more nodes present and more antinodes present as well, and this would be achieved at a higher frequency. For a string that's fixed at both ends with a length L, we can calculate all of the harmonic frequencies that are possible for that system using the equation in green right here. Given that the wave speed is constant for a constant medium, we could also calculate a wavelength for each harmonic mode as well. Standing waves can also be created for sound waves that are traveling in an air column, and this is the principle behind most musical instruments. There are 2 major types of air columns that resonate with a resonant frequency. The first is called an open-closed air column, and that's the type of air column that's used in instruments like the saxophone, clarinet, trumpet, and our own voice, where we have one end that's closed and doesn't let any of the air vibrate, and one end that's open and lets the air vibrate at a maximum displacement. We would say that we have a node at the closed end where the particles cannot be displaced from their equilibrium position, and an antinode at the open end where the particles can be displaced a maximum from their equilibrium position. And we can use this formula to calculate the frequency of an open-closed air column at different harmonic levels. It's important to note that this equation is different than that for the string that is fixed at both ends. The harmonic numbers for an open-closed air column will only ever be odd integers, and it has this little sneaky 4 that snuck into the equation as well. So, for the fundamental frequency, we would still have n equals 1, and we would have a node at the closed end and an antinode at the open end. But the next harmonic that this air column can possibly accommodate, the next pattern that would fit in this air column with an antinode at the open end and a node at the closed end would be the n equals 3 harmonic. This would be known as the third harmonic of the open-closed air column, but the first overtone. It's the first harmonic that is present beyond the fundamental, and it has a shape like what you see here. If you want to try to better understand what the air particles are actually doing in an open-closed air column, you can try to take a look at these figures here. We have our fundamental frequency on the left for an open-closed air column, and the air particles move a lot at the open end, but they do not move very much at the closed end. On the other hand, if we jump all the way up to the 7th harmonic, the n equals 7 number, the third overtone for an open-closed air column, we would see that there are more points throughout the air column that experience 0 displacement, more nodes, and also more antinodes occurring at a higher frequency. On the other hand, standing waves can also be generated with sound waves traveling in an open air column, a tube of air that has both ends open. In an open air column, the formula feels a whole lot like the string fixed at both ends, except this time, instead of having nodes at both ends, the open air column would have antinodes at both ends. It would have a maximum displacement at each open end, and you can calculate the different resonant frequencies for an open air column by using the equation shown here, where n can again adopt any integer values, and we have the formula for the resonant frequency with a 2 in it. In this case, the fundamental frequency would have an antinode at each end where the tube is open to the air, allowing for a maximum displacement. And this is the principle behind how many other musical instruments like the bassoon, oboe, piccolo, flute, tin whistle, and organ work. That'll cover everything for our unit on waves. Thank you for your attention. Good luck in the coming days, and I'll see you in the next one.